All right. So my name is David Korczynski, and I'm a PhD student at University of Oxford. And today I will be talking about capturing malware propagations with code injections and code reuse attacks. And the work that I present here is teamwork by me and Heng Yin from University of California in Riverside. So, a brief introduction. Basically, at the most fundamental level, what we're talking about is automated dynamic analysis of malware. And what we're really interested in is how do you capture the malware execution inside of your sandbox in the context of code injections, in the context of code reuse attacks, and stuff like that. Specifically, we're interested in how you capture instruction level execution traces of malware, the concept of code injection and code reuse attacks, and also how you capture dynamically generated code in your sandbox. And all of the techniques that I present in this talk has been implemented into a system called Tartarus. And we have evaluated it against in a bunch of different data sets. So when I talk about automated dynamic analysis of malware, what I mean is you have some sort of sandbox where where you put your sample in, you execute it, and you gather some sort of information. You can gather information at many different levels of granularity. You can have very coarse-grained information collection where you look at what are the changes in the system before execution and after execution. And you can also have a much more fine-grained approach where you look at, for example, the API calls or the system calls performed by the malware, where you try to get the instruction trace in order to do some very detailed behavioral analysis. If you want to do selective symbolic execution or so, you also need to have the instruction trace of the malware. And well, you all are probably very familiar with Cuckoo Sandbox that tries to log all of the API calls performed by the malware. There's a big difference between whether you collect this coarse-grained information or you collect the fine-grained information, which is whenever you want to have the fine-grained information, you have an implicit definition of what instructions inside of the sandbox belong to the malware execution and what instructions inside of the sandbox belong to the benign code execution. You obviously don't want to report all the system calls happened within all the processes on the system, but you want to collect those system calls performed exactly by the malware. This is essentially where we started. The base point was then we asked the first problem: how do you capture the most fine-grained trace of the malware within your entire sandbox, within the entire operating system? That is the first problem we look into. How do you collect an instruction level execution trace of the malware? And a first try may be to just execute the malware into a sandbox, collect all of the instructions executed within the process that represents the malware, and if we visualize what you are going to get, you will have a system with a bunch of different processes running on. All of the gray arrows represent benign code execution, and all the red arrows represent malicious code execution. There's nothing surprising here, and well, you're going to get all of the instructions executed within the malware process. The question is really, how realistic is this? How realistic is it that the malware stays within its own process and doesn't really do much else? Uh, Fact is that the malware usually infects the host system. When you execute it, it starts to inject into other processes. It might throw some code reuse attacks to do these injections and stuff like that. On the right side, you see a system-wide control flow graph of the Timber malware and how it propagates within the entire operating system. So it starts in its own process. Then first it performs one code injection into a Windows process called winwar.exe. And the code from winwar.exe then further injects into another process, explore.exe. The code inside explore.exe then starts to inject code into all of the different popular browsers. What is important to realize here is that the code in each process, it doesn't terminate after it has performed code injection further. The malware may actually distribute a lot of different behaviors to a lot of different types of processes on the system. So for example, the code in explorer.exe will continuously look at whether the code in all the browsers are still running and stuff like that. And you may have a lot of communication between the different processes. In addition to this, we also have a lot of blended in terms of like decryption and unpacking and so on, all during the way. And the malware does this infection into the system for various different reasons. it may not just be because of privilege escalation. It doesn't just inject into a process because of that. It can also be because of evasiveness in order to avoid being analyzed by host-based intrusion prevention systems, and also just to divert from the sandbox. For example, so the sandbox may report the sample is actually benign because it didn't see that the malware injected into some code where all the malicious stuff happened. In our evaluation, we actually found that more than 40% of the malware samples we analyzed in like a random data set we collected from VirusTotal executed in more than one process. So the main problem was really, the initial main problem was really how do we capture this in a very generic and general manner. So if we visualize what is happening, you actually see start in one process, and then you see the malicious code execution happening in many different other processes, not just the one itself. So clearly, it's not sufficient to just capture the execution within the initial malware process. What we could do is, a second approach might be we identify all the common ways that malware inject into other processes. There's a bunch of common approaches in Windows where you use create remote thread or resume thread or something like that. And they are very well documented, and it will take you a certain step. But in order to argue against this, I mean, clearly it's not a very general or elegant solution, but in order to argue against this, I would like to go through an example of a malware that was discovered in 2013 uh, called the Gapz. The Gapz malware, it uses a code injection technique called power loader. If any of you are familiar with it. The overall execution of Gapz is shown on the right. It starts up in the, the dark circle in the upper left corner is the entry point. What first happens is that the malware executes, then it decrypts itself inside of its own process, so it unpacks itself, some people call it. After the unpacked code will then inject into explorer.exe, which is this trusted Windows process. The way the malware injects into explorer.exe is by using the API calls send notify message, and it also overwrites a bunch of function pointers in explorer.exe using the API call set Windows long. So this is very different from just having a create remote thread in a different process or something like that. And yeah, what happens inside of explorer.exe is that it hijacks control over a bunch of indirect branch instructions. These indirect branch instructions are redirected to a bunch of gadgets that will override the stack with a ROP chain, and the ROP chain then continues execution with shellcode, and we just see more and more execution inside of explorer.exe. To show you what specifically happens, here you have the, oh, can you see that? But here you have the vulnerability in explorer.exe. It's not really a vulnerability in the sense that by injecting into Explorer, it doesn't gain escalated privileges. It doesn't just suddenly get admin rights, but it still starts to use, well, what is very similar to a traditional exploit. What happens is that there's a call in the first basic block to get window long. This is code inside of explorer.exe. The return value of get window long is put into ESI, and then the first instruction in the second basic block dereferences ESI and puts the value in EAX. What then happens is that there are 3 indirect call instructions that jump based on the value on EAX. So what is returned by get window long is actually like a double pointer, which eventually points to a struct that has 3 different code pointers in it. Okay, and each of these 3 indirect calls, the code pointers, will be executed. This particular code is inside a message handler in Windows, in Explorer.exe. So any malware or any other process can actually trigger this code on demand. And what is particular here is that any process can also control what is returned by get window long A. So inside of the Gapz malware, you have this particular code where there's first a call to set window long A. That's the first function call here in the second basic block. And then there's a call to send notify message. These are the particular, there's a little bit more to it, some pre-work and stuff like that. But these are the 2 function calls that actually makes the injection happen. So when this malware came out, unless some people had already reverse engineered this and all this kind of stuff and understood it, but it bypassed all the host-based intrusion prevention systems. Also, dynamic sandboxes, they wouldn't know that the code actually executed into Explorer, so they had no idea of knowing that actually a code injection happened here. So suddenly a lot of understanding of the malware was missed by all these automated analysis systems. And just what happens when Gapz calls this send notify message, this code is called again, the handler inside of Explorer.exe, and here you see the gadgets that are redirected to by the malware. The first gadget is a gadget that loads into EDI an address that is close to the top of the stack. The second gadget sets the direction flag, and the third gadget executes rep move SD. In this case, which will cause 94 bytes in hex to be 94 bytes in hex to be overwritten on the stack. Since the malware also controls ESI, and it has just performed a gadget execution that will load the address of the top of this, an address close to the top of the stack into EDI, it will actually copy the content of ESI onto the top of the stack. And the malware, being in control of ESI, has obviously pointed it to, well, a ROP chain that it has previously written. So that's how the Gapz malware hijacks execution of Explorer.exe without using a traditional code injection sequence of API calls. When you think about this in terms of you want to collect the instruction execution trace, suddenly it becomes a little bit tricky with what instructions are actually part of the malware execution. And it's not just, now it's far from being the instructions just in the malware process, but we suddenly have a bunch of instructions, a bunch of gadgets inside of Explorer.exe, which is arguably also a part of the malware execution. And this is really what we want to capture with our tool. We really want to have a more refined understanding of what is the instruction level execution trace here. And just to get an overview again over Gapz, it starts by decrypting itself, then injects into Explorer.exe using this untraditional approach. The injection in Explorer.exe is specific to Explorer.exe. It relies on specific code constructs inside of that program, but it doesn't get any escalated privileges. And yeah, not every instruction that arguably belongs to the malware execution trace is explicitly represented in the malware, because the gadgets are very much a part of the malware execution. They are an important feature of it, but they are certainly not represented in either the disassembly of the unpacked malware or so. The malware has several waves of dynamic generate code. So surely we can't just hook all these create remote thread and these types of common approaches to code injections. Instead, we say if you want to have a very general approach in your sandbox and you want to actually have a very precise collection of information about what the malware does, you must use some form of, or at least you should use in an elegant approach, you should use an information flow based approach to trace whatever the malware is doing. And that's like one of the key things of our paper is you have to use that in order to capture these advanced code injection behaviors. I want to emphasize here that the code injection by Gapz is not one of a kind. We have seen more code reuse, like injections that uses code reuse in order to execute code in a remote process, even if the remote process does not elevate its privileges to admin or so. So the way we suggest that you should trace the malware is that you use dynamic taint analysis to trace the execution. The specific approach is that you taint the malware when it's loaded into memory. You taint all of the memory when the malware is loaded. And then you execute your sandbox. And for every instruction executed within your system, you include it in the malware execution trace if the memory making up the instruction is tainted, or it is an indirect branch and the value that determines the destination of the branch is tainted, but the destination itself is not tainted. In this way, you can capture all these code reuse gadgets and so on. And you also have to taint the output of each instruction in the execution trace, because sometimes you will see malware when it does this decryption of itself. You will often see malware, either using some cryptography to generate some values or stuff like that, which is not explicitly represented in the original malware image. So this is our suggestion for how you should actually trace the malware in your sandbox. And then what you get is you get this for free. You get you then start to see malware execution in whatever process it is on the system. You have actually started to follow the malware execution completely without doing any sort of hooks or anything like that. And the next question you then have to tackle is, if you want, now the next approach, now the next thing we want to do is we want to essentially uh, produce a system-wide control flow graph of the malware execution as shown on the right. So now we have to identify, when we have this sort of like blurry instruction trace where some execution happens in one process, some execution happens in a different process, and so on. We want to have a little bit more reasoning about it. We want to have a little bit more understanding of what is actually going on. And one of the main questions you can ask here is, where does code injections actually happen? Because a lot of the times, the reason we see different executions the reason we see these sort of like transition from one process to another is because of context switches, not really because of a code injection. It doesn't show that there's a transition from one process to another. It doesn't necessarily mean there's actually a control flow transition. So we come up with a suggestion for how you identify, once you have this system-wide trace, how you identify where code injections happen. And the way we do this is we give a model of code injections where you have we have a code injection is composed of a tuple of 3 elements: an initiator instruction, a catalyst, and a target instruction. And the target instruction is identified whenever we observe new, I should say here, non-code reuse, malware code execution in a remote process. And when we have identified a target instruction, we trace back in the malware execution trace to the first API call that branches to something different than something in the malware execution trace, and label that as the initiator instruction. And then we look for if there are any code reuse in between the target and the initiator instruction, if there's any code reuse in the in the process of the target instruction. And then we label that as the catalyst, because we argue that the code reuse have been used to like leverage the execution of the target instruction. So on the right, you see how this approach is used against the Gapz malware, where you clearly see, I don't know if you can see it, but what you see is that the initiator instruction will be identified as the send notify message. You then have 3 gadgets collected that are each of these indirect call instruction, indirect branch instructions. We also included the gadgets that we also include whenever we see a code reuse. We also include the gadgets, and you see the gadgets included as well in the malware execution trace. And then you see a bunch of other small gadgets, which are all these red, basically return-oriented programming. So you see this in the malware execution trace. You actually have a complete understanding of the code reuse attacks used in the code injection. And none of these code reuse attacks are explicitly represented in the malware. So there's a completely new definition, I would say, in terms of the malware execution trace. But it's a very important part of it, because this constitute, if you want to, for example, pipe this to a host-based intrusion prevention system, it's very important to understand what happens here in this code injection. A second thing we look into is how to capture dynamically generated code, which is has been a very common feature in malware analysis. So you often use that for automated unpacking and so. And the general approach is to split the code execution into multiple code waves. The way previous work does it is by looking at, they set the first code wave to be the malware when it's loaded into memory. Then they look for all the memory writes performed by each code wave, and whenever an instruction is executed that was previously written by a prior code wave, then we have dynamically generated code. This works really well in the context where malware explicitly writes the code. But when you have, for example, that the malware uses benign code in order to generate its malicious code, this type of model will not work at all. However, our approach is well tailored for that, because we have a information flow based approach. So we are kind of like, so we have an approach that's well tailored to identify dynamically generated malicious code independent of who wrote the actual code. And the way we do this is that we keep a shadow memory for each process, with a shadow memory holding a given code wave. And the initial code wave is the malware when it's first loaded into memory. And whenever we observe an instruction that is inconsistent with the shadow memory of the current process, then we have a notion of dynamically generated code. So you can think of the first code wave as the malware when it's written into when it's first loaded into memory. Whenever we see an instruction that is then not in this like snapshot, which is the code wave of the initial process, it means that something new malicious memory has been generated. And this is a very general definition of a dynamically generated code. So whenever we observe, dynamically generated code, we clear the shadow memory, we scan the process for new tainted memory, and this is then the next code wave. Putting it all together, our information flow-based tracing, our ability to identify code injections, and our ability to identify dynamically generated code, we get what we call a system-wide control flow graph. And what you see on the right is produced by our tool Tartarus. It very clearly shows that the malware first decrypts itself with one wave. It then performs a code injection into explorer.exe using some system calls API calls we had no hooking on or nothing like that. We see that there's code reuse attacks. These code reuse attacks perform this writing of the shellcode, which is the wave 0 in the explorer.exe process. It only has 58 instructions and then transfers execution to a new wave. So it gives you a very, very precise and refined view of the malware execution inside your system. And we have tested this against 30 different. We have tested this in several different ways. And one of the evaluations where we put a lot of effort in was tested against a lot of known code injections and a lot of malware that we know performs code injections. So all of this is against, you can say, ground truth applications. We tested Tartarus against 10 synthetic injections, which are well known. 4 of these had code reuse in their injections. And we compared it to a disassembler code disassemble, which was presented at CCS 2 years ago, which uses create remote thread, hooks create remote thread in order to follow malware execution. And we also compared it to Cuckoo Sandbox. Our tool Tartarus found the code injections in all of the samples and also identified code reuse in all of the code injections that have code reuse, and didn't identify code reuse injections in any of the other samples. We found all of the code injections. We did find a few false positives, meaning we sometimes see malware execution in a process which is not really malware execution, but usually what you see is 15 instructions executed in this process. They look potentially a little bit arbitrary, but 10,000 instructions executed in this other process. So it becomes quite clear where the real malware execution happens. We also did some performance evaluation. The performance is carried out on on a small laptop. There's not too much to say. It takes very arbitrarily from 30 seconds to 20 minutes to analyze a malware sample, and in order to find these code injections in our data set. What is potentially quite interesting is, what you see on the y-axis here is the size of the CFG as it is produced. So when it's 100%, we have uncovered the entire system-wide CFG. So we'll often see that there's like a steady area where we don't recover anything new. And this is usually when the malware decrypts itself and so on. Just a quick summary. We present a new approach to capturing malware execution traces that is based on dynamic taint analysis. We present a technique to identify dynamically generated malicious code, and we present a technique to identify code injections and give valuable insights about the intricacies of each injection. We have implemented techniques in a system, and our results show much improvement in capturing system-wide malware propagations. That's all I have, and I thank you for listening, and I'm happy to take any questions.
I want to first thank you for your great work. I'm Sina from University of California, Riverside. And my question is, did you do any sort of false positive analysis?
Yes, I didn't go too much into it now, but we did. There's there's a lot of discussion about the false positives. We explained clearly in this evaluation where we test against malware that we know what code injections they perform. We show clearly which injections we saw that were not described that were not actually happening in the malware and so on. And as I said, usually it's not that big of a deal. We don't really, yeah. Usually, what you see is the malware will inject into all the processes that it should, but you also see like 10 instructions executed in SVC host or something. But again, 10,000 instructions in the actual process that it injects into. But there's a discussion on false positive in the paper, and they occur. It's very clear though where they occur.
Thank you.
Thank you.
Jim Peng Wei from UNC Charlotte. Excellent work. Thank you for the presentation.
Thank you.
So my question is about the how recent are the malware samples that you used? Did you see a trend, for example, over the years that this
It's
technique is used more and more, or did you collect that data? Thank you.
I mean, that's a really interesting. I think that's a paper in itself, I would say. But that's a really interesting evaluation. Can you see a trend in this? And we use malware samples from a lot of the evaluation was put into actually ensuring the correctness of our tool, and that was based on malware samples from different ages. We did do an analysis on like 900 something samples from this year, and we show that a report from Palo Alto in 2012 reported, I think, about 20% or so code injections, where we found 40%. But I like the idea that you say of doing a longer study. One interesting aspect about that is that last year in S&P there was a paper which showed that hackers have not really gained that much complexity recently. It's called which it was by some people in I can't Eurocom, I think. And I think they showed like hackers have not been much more complex in recent years. But I think if we take this approach, we will probably see it has gained the infections that malware do, and the system has actually gained a lot of more complexity. But I haven't shown that yet. Uh, thank you for the suggestion, though.
Excellent. Thank you.
Hey, thank you for your presentation. Lucas Drazel from UC Santa Barbara.
Mhm.
Is or do you intend to make your tool public for testing?
Yeah, I don't see any. I would love to do that.
Okay, thank you.
I don't know if it will just be like open source thrown out, or if I will make up a service or something like that. But this is gonna happen in the near future. If you have something explicitly, just write to me, and we will get it as such. If you're doing something right now, then do that.